Jan, thanks for sitting down with me here at the Dublin Longevity Summit. So I really enjoyed your talk
Thank you.
yesterday, and I'm hoping we can dive into some of the concepts that you brought up. So one of the things I wanted to ask you about
Mhm.
is, so you come with a physics background, and early in your talk you mentioned the role of stochasticity or randomness
Mhm.
in longevity and mortality in particular. So maybe you can talk a little bit about that. It's something that I think we don't really, as biologists, appreciate a lot
Okay.
of the time.
Well, let me start with saying that actually it came from the free radical field. And in a way, that was, back then, actually sort of the trivial thing people thought, right? Damage of some sort,
Right.
which is something random. So we sort of come full circle from this. And now it's sort of a concept which maybe people have more problems with or believe less in than they used to. But for me, it's sort of coming full circle, right? I started out trying to measure oxidative damage, thinking that if you measure the right oxidative damage, you're going to be able to find the driver of aging. If you remember back at the vicious cycle theory, there was this idea that you get autocatalytic damage, more damage causes more damage, and that gives you exponential damage, and that gives you
Right.
exponential mortality. But the truth is that you don't really find exponential damage, in most systems. So what you need is sort of a way to explain how non-exponential cause can cause exponential increase in mortality, right?
Right.
And there's an elegant way of doing this, which comes from physics, which is that if you consider physiological function, right, like your body's responses to environmental and intrinsic random events, stresses, eating, glucose goes up, insulin goes up, glucose comes down, overshoot, and so on and so forth. If you describe this, how physicists would do it, you describe it in a linearized system and you say it's a sort of series of oscillators, basically. It's things that return back to some set point when you let go of them after you perturb them. And that's how physiology should work, right? Now, the way to describe this is to say you have some sort of phase point in a potential. You have a potential. The potential is all the physiology, all the gene regulatory networks, all the metabolites, the physical structure that produces a returning force that is essentially evolved to keep you in a set point compatible with life. When you get older, that potential becomes flatter. In other words, you get worse at this. And that is something which even the Victorians, like
Hmm.
the next concept after there is some magic force of life that runs out, that the Victorians came up with is to realize resilience goes down. Old people are
Right.
easier to kill.
Right.
You do a stressful thing, you might kill an old person. And the young person, if his training response and gets stronger, an old person may never recover and die. And that's a sort of just very fundamental fact about aging. Now, if you describe this as having a sort of potential well that describes, it's a high dimensional, it's like, thousands and thousands, probably millions of, processes that are, or at least metabolites and molecules involved. You describe this potential well and say, okay, so normal physiology is in the center somewhere at the lowest point, and every perturbation perturbs you a little bit, it moves you out to the sides, but then the system sort of returns back to equilibrium, right? Then there is this called Langevin equation. It's basically Brownian motion, random noise with potential. There's a way to calculate the probability that you accidentally escape this potential. And that turns out to be exponentially dependent on the height of the potential. You can get that, you can make a hand-waving argument from Boltzmann distribution, or you can just solve Langevin equation. And fundamentally, as you make the well lower linearly, the probability of escaping increases exponentially.
And in this case, escaping would mean you die.
Well, so what escape means in this case is you get over the hill and then you want to return back to equilibrium, but instead you either find another equilibrium, in other words, you irreversibly change,
Hmm.
or you fall down, some self-amplifying process. If you think about what that means, you have a physiological set point, you get perturbed beyond a certain point, and then things get worse and worse and worse until eventually you die,
Right.
because you have a positive feedback now, right? So the perfect example for this would be cytokine storm. You have an inflammation, and normally you remove the source and you return back to equilibrium, and the inflammation goes back. You go running, you have increased inflammation, you have a training response, everything's fine. You are old and you get exposed to the wrong virus, you essentially get an inflammatory response. It just self-amplifies until the tissue just fails, dies,
Right.
the organism dies.
Right.
And so this can either be an irreversible change to another state, or it can be in the self-amplification exponential departure from normal physiology, which is we call disease, and then it kills you, right?
Right.
Okay, so height can give you a very elegant way where a linear change in something will give you an exponential change in the risk of failure. Okay, so it's a mechanism that explains this linear to exponential. So that's elegant. If you're a physicist, you like this. It's also how physicists can't really deal with a lot of things. Is how physicists describe most things: linearized dynamical systems. It's like ecosystem, linearized dynamical system. World economy, linearized. I mean, that's what we do, right?
Sure. So let's take a step back then, and maybe you can put it into the context of. I mean, if you think about the aging process, or the things that lead to this increased risk of mortality, lifespan. So we've got, it's under genetic control for sure. It's under environmental control, and then how do you see those things interacting with this randomness component?
Sure. So you asked about damage originally. So the argument, of course, is that there is an abstraction of damage, a type of damage or entropy that accumulates that causes this potential to get shallower, right? That's the idea. And so that's aging rate. So the mortality rate doubling time basically is directly related to how long does it take for this potential to go from a youthful, deep, safe state to becoming, eventually zero, at which point death is inevitable.
And how does genetics fit into that?
So the genetic fits into this because all the processes in the system are evolved to do two things. When you're young, they evolve to have optimal function. In other words, for instance, your physiology works. And then there is, some sort of rare stochastic events that degrade the performance over time. And those are also under genetic control. And so this lowering of this potential doesn't have to be something magic. It could be something simple like you have cross-linking in your blood vessels, so they become stiffer, so your blood pressure control gets worse. That's a perfect example. There's a stochastic event. It happens somewhere. It causes, collective, counts of the number of cross-linked molecules. You add up on them, and you basically say, what is the total fraction of these molecules that can be cross-linked, that are cross-linked, that gives you how much that particular aspect of the potential has degraded, right? And of course, the speed of cross-linking is under genetic control, right? So maintenance mechanism, all the same things we always look at, DNA repair, somatic, senescent cells, even epigenetic drift, those are all examples where you have, as part of the normal function, a small amount of irreversible change, right? So the methylation sites, for instance, you have methylation, demethylation. Over time, there's a systematic trend. That's why you can make a methylation clock, right? That means it doesn't return back to the perfect state, as you activate.
Or the initial state,
the initial state or the youthful state. It just is slightly different. The interesting thing about this is it's the aggregate that counts. There's not, like what sort of, in my view, the mistake we used to make is that everybody said my type of damage, for instance, is the essential one. And if I just remove mitochondrial DNA damage, everything will work. And so this is not needed here. You have all of the collective, damage or change, irreversible change, the entropy that stays in the system essentially eventually degrades your physiological performance.
So you consider all of the different types of damage, and probably that people have proposed as mechanisms of aging, and probably others that we don't know about yet, those sort of all contribute to this entropy term.
Yes, exactly. You add them all up. I mean, if you want to write down the formulation, you're saying there are lots of really rare, once-in-a-lifetime transitions somewhere that cause small changes in the nonlinear terms. But, Peter will be better at explaining this than I am. But fundamentally, the idea is that, every time you switch something on and off, it doesn't, there's a chance that something won't fully go back to where it's supposed to be. You have a macromolecular modification that doesn't return, or you have a structural change, or you have, an informational change, like a mutation, where you then less good at some aspect of physiology than you were before by a tiny margin. But the interesting thing is that if you add enough of these tiny individually rare events, you get a very simple description, which is what physicists like, which is the total sum is all you count. You're going like, is it 1,000 or is it 10,000? That matters. It doesn't matter what exactly happens. So you can elegantly ignore all the details you don't possibly know about.
Yeah, and so I mean, you said that the damage itself is somewhat stochastic, and when it occurs, how it occurs, how bad it is. So how do things like lifestyle fit into this then? I mean, that would go under environment, but they modulate the likelihood of a damage event happening in some way.
Yeah, certainly. I mean, so for instance, perfect examples, I just talked about glucose, right? So we all know that anti-diabetic drugs are one of the things, and anti-diabetic lifestyle interventions, preventing, not eating too much sugar, reduce the, you're wearing a continuous glucose monitor, right? So that's a perfect example. You have these random fluctuations. But HbA1c...
They're not random. I mean...
Well, no, but they're not random because they cause an effect. But if you look at them as time series over time, they are fluctuations.
Sure.
Right? They're by lifestyle, by
Sure.
choice, by random events. Like whatever, you miss the bus, you have your burger half an hour later. Not that I suggest you eat burgers. But anyway, so those fluctuations, and HbA1c already integrates them, right? Like we measure what's the average of this. Now, this is another layer of the same idea, is that over life, you integrate these, in forms of rare individual damage. So for instance, cross-linking events in blood vessels, or possibly metabolic changes in mitochondria somewhere that have to do with blood, sugar spikes, and not all of them reverse perfectly when your sugar comes down again.
Right.
So therefore, every time you have certain lifestyle decisions, you don't sleep well, you have inflammatory signaling, you get exposed to a virus, you have an injury, you play with radioactive isotopes, you're causing some sort of increase. Well, old-fashioned biochemist, right?
Right.
But yeah, no. So that would be how that works, right?
So let me see if I can restate this, and you tell me how much I've gotten wrong. So, so aging can be considered as the, at least in part, the accumulation of stochastic damage events that are the likelihood of those occurring, and potentially the degree to which they are damaging can be influenced both by genetics and environment. Environment would include lifestyle, but also lots of other things we're exposed to. And so how does that fit into this idea? So what's causing the decline in resilience, though? So you've got the damage that might push you out of homeostasis. Right?
So the damage is the decline in resilience, right? So perfect example, we talked cross-linking as an example, right? So your vascular system will respond to different demands by changing blood pressure. But if your tubes get stiff with time, that becomes more difficult. The heart has to work harder, there's less buffering. And so therefore, the cross-linking, which is individually, if you take one molecule and you go, what is the probability of this site getting a sugar cross-link, like an end product attached, is very random. It's very rare. Most of them never get modified, but some of them get modified. And the total number of them, I can tell you what is the degree of cross-linking. I do some sort of test of this.
Right.
And that directly affects your ability to deal with blood pressure variations.
Got it.
Right? And so the same is true for like mitochondrial changes, right? Like mitochondria may change the substrate, as we heard yesterday. There's differences in how exactly the energy production in the mitochondria works. It doesn't even need to be a mitochondrial DNA deletion, right? It could just be a slight change in mode, right? So this concept of damage in this case is sort of generalization. It's all small, stochastic, individually rare events that somewhat detriment your resilience.
I see. So in this case, I think this is partly why it's really important to define what you mean by damage, because it can mean all sorts of different things. So in this case, in this model, damage is the thing that leads to the decline in resilience with age. And so then what is causing the sort of fluctuations that might push you over the edge? Are you calling that stress then in this case?
So there are random fluctuations. We have this preprint out where we call that the factor that scales is the effective temperature, right? And it makes a strong statement to say this. What we're basically saying is there is a scaling factor that is, species and potentially individual dependent, that tells you how much of these fluctuations you have. And that goes beyond just your blood pressure or your glucose. That's what like all physiological processes. And from the analysis of some epigenetics data between different animals, it looks like this is a species-specific, not a pathway-specific thing. Now, that's not trivial, right? So the idea that a mouse has fundamentally different randomness and stochasticity than a human, rather than energy metabolism is fundamentally different in the stochasticity to cell cycle.
Right.
Cell fate is not a given. It's not, that's an observation and a hypothesis, testable, and we need to get better data to test it, rather than something you would trivially expect. But if you expect this, then you have two factors, and that's the nice thing about physics. We can reduce everything to like two numbers, right? All this biology, who needs to know it? And that is, you have a temperature, which tells you how much fluctuations you have. And then you have a height of the potential that declines at a linear rate.
And that decline is caused by the damage.
So you have a damage accumulation rate, a thermodynamic efficiency factor, how much of your metabolism causes irreversible damage. And then you have a temperature that gives you fluctuation. And if you put those two things together, you can perfectly create a lifespan curve.
And do we have any understanding of the biology of that temperature factor? What is driving it?
So in the context of the epigenetic data set, and we need to do this in other contexts, it's probably something to do with how completely you activate and shut down transcription, right? It's something to do with, for instance, methylation, demethylation has to do with histones. It has to do with essentially how much fidelity you have in your transcriptional machine, how fast you switch genes on and off, and how completely you switch them on and off, because that changes essentially the transcriptional and epigenetic stochasticity, the amount of randomness you have in gene expression.
I see. And does that change with age?
So
does that term change with age?
To the extent that we know from this data set, which is fantastic, it's a really cool data set, but it's has limits.
Sure.
We think not.
Okay.
I mean, or that in the model we don't put that. But again, also you keep the model as simple as possible, right? You basically assume that it's
limited, the least amount you need to do to the model to get it to recapitulate the observable data. Yeah.
And it does some really cool thing to lifespan. So the damage accumulation rate, or the thermodynamic efficiency factor, the speed with which the potential drops, right? Degrades. It tells you the maximum lifespan, because by the time the potential is zero, no amount of stochasticity is survivable.
Regardless of,
you're going to
fall
down
lucky
the hill.
they are, or unlucky they are.
So that's the maximum lifespan of the lifespan curve. And the temperature tells you how square the curve is. If you have high stochasticity, high temperature, and it's a sort of an abstraction of the idea of the effective temperature, then you basically get random escape, and you get a lifespan curve that looks like a shitty worm experiment, where you don't it's like this, right?
Yeah.
And if you make the temperature zero, which is impossible, everybody survives to the maximum lifespan and then dies, right? Because there's no stochasticity, so as long as there's potential, you're going to stay.
Right.
So basically the two parameters tell you how the lifespan curves look like. One stretches the curve, because it changes. It's basically just the time translation, right? You stretch time by 2, it takes twice as long for the potential to degrade, so the maximum lifespan gets twice. And the other one tells you the sharpness of the turn. And if that's true, and if you can measure those two parameters, you can make a protocol to measure them, then you might find, for instance, control variables or genes that affect them. Temperature and maximum lifespan controlling, thermodynamic efficiency. And that would be a cool sort of way to think about drug discovery.
So let's take a step back and make sure we've got the vocabulary here, the way you guys have defined it. So tell me how you define temperature in this 2-parameter sort of model that we've been talking about.
So it is the scaling factor that is species specific, that tells you how much stochasticity, how much random noise, how much fluctuation the system intrinsically generates in interaction with the environment.
Okay.
So how much attempts are there, how much physiological returning is required to sort of escape the well, basically.
And is this, so when you're talking about the oscillations, right, is this temperature term affecting the frequency or the height?
Amplitude.
Or
I guess both, but the critical thing is the amplitude.
Because that's what pushes you over the edge.
Yeah. I mean, I guess it's sampled from a distribution. But it's basically it essentially scales the height, right? If you have more noise, you can overcome a larger barrier.
Okay, and that's species determined.
It is species determined.
What's the other term?
The other term is essentially a linear decline between youthful, strong physiological returning forces and eventually maximum lifespan, where you have no more returning forces, where any perturbation will kick you over the edge and kill you.
Okay, and that is not species determined?
That's also species dependent. Of course, right? Like a mouse lifespan, maximum lifespan is much shorter than that of human, and the different bats have extremely long ones. So the maximum lifespan is clearly determined by this. But the maximum lifespan is just basically, if you want to get it from a lifespan curve, you would say it is basically 1 divided by the maximum lifespan, right? That is the rate. So every year you lose what percentage of the maximum resilience you have. It's the loss of resilience. But it is motivated in this case as the rate of small random entropic events that you can't remove, that remain in the system.
I see. Yeah. I mean, again, I think this is one of the challenges when biologists try to talk to physicists, right? Is because, of course, my mind's immediately going to, what's the biology underlying this?
Yeah. I mean, if you want to that's why I went for the example with the damage. I mean, you could.
I mean, you're both. So I didn't mean to imply you're only a physicist.
Yeah, no.
you know what I mean?
Yeah, sure. But it's the macromolecular damage on some level. It's more than that, right? Like for instance, it can be drift in beta factors of epigenetic sites. It's not damage in the traditional sense, but it is entropic change that might detriment some process.
Which is damage.
Which is damage, exactly. So there's a sort of convergence of concept there.
Okay.
Right? We used to think of this only as macromolecular damage.
Right. Yeah. Okay, so let's come up a little bit. This is all going to tie together, but maybe you can define how you think of biological age or biological aging, and is that something you think we can measure now, or we will be able to measure in the future, or is it even a real thing? I guess.
I mean, absolutely, it's a real thing, right? So the problem is you can, of course, try to measure, for instance, this entropic change. One animal has more, one has less. And that's basically what the whole thing about measuring macromolecular damage was all about. It's just extremely difficult because you're measuring always the same problem. You're measuring very rare, very low frequency events, and there are many, many different types of them. And then you get into this situation where you're saying, okay, so is this damage more important? Is that damage more important? If I protect from this damage, will I live forever? Of course not, because there's lots of other things that are happening.
Right.
And I think that was the sort of fallacy of, like 20 years ago when we were like, oh, mitochondria targeted antioxidant will make the mitochondrial DNA safe, and then we will get maximum lifespan extension, and it just didn't really happen. But it's an interesting way to think about this, because if you think about the problem as a dynamical process, you can ask what's the signatures of this change. And what I just said is you have this, barrier events, and you can essentially say, what does it look like when a system fails this way, right? Which we just described. And it turns out that it's actually exactly how we think about the failure, for instance, of ecosystems. It's a pretty universal way to fail. And what it leads to is signatures of failure. For instance, a process or a phenomenon called critical slowing down, where close to the transition, the returning force just gets weaker, and it takes longer for the system to return back to equilibrium. Now, that's very measurable, right? If you take a continuous glucose monitor and you do a glucose tolerance test, you essentially do a single-dimensional example of this. You're saying it should take less than an hour to get your glucose back after a standardized challenge. If it takes 2 or 3 hours, then you're pre-diabetic. If it never returns, you're insulin dependent. And so the whole point about this is that you can use these dynamic measures to quantify aging. So with longitudinal data, you can use ways to measure this in the data, for instance, through autocorrelation function, to get a dynamical snapshot of how well resilience across domains works.
Right.
And that is a measure of the age of the organism, because it directly relates to the probability that an eventual challenge or a combination of challenges might kill you.
Yeah.
Right.
I think this is really important, because this is kind of a very different conceptual way to assess biological age than something like a methylation clock, right?
It is, yeah.
Because I think what you're saying is what the core feature of biological aging could be is the ability to return to homeostasis after some sort of damage event or challenge event, right?
Yes. And I think that's, it requires longitudinal data, which is a challenge. But I do think, I'm very excited about building sort of predictors or clocks you can, whatever, apply AI to predicting outcomes. Based on that, based on the measuring the lack of resilience, not in a single domain, but you can do glucose tolerance, but to get a high dimensional data set and look at the general patterns of loss of returning forces in the system, and turn this into an aggregate measure and say, okay, so that's age. Because what exactly fails is different in different people.
Sure.
Right? Like, so because of your genetics and your environment and your exposure, different people fall into different failure modes that then eventually manifest the disease. But the underlying lack of resilience, the underlying loss of resilience, I think is a systemic thing. And that's what we want to measure and learn how to manipulate.
How many of these sort of dynamic processes do you think you need to measure to get some sort of holistic assessment of biological age? And so what I'm meaning is, if you think about the glucose response that you mentioned, most people, maybe all people, will show a change in that ability to, respond to a glucose challenge as they get older. But they're dramatically different trajectories, right? There's some people who develop diabetes early in life, and so for that particular parameter, their resilience is perturbed early on. whereas other people can go the vast majority of their life and still have, relatively normal glucose response. So presumably it's not only one, not going to be able to only measure only one dynamic process. And so I'm trying to get an idea of, because one of the appeals of the epigenetic clocks is we can just measure one thing and it'll tell. I mean, obviously, I don't believe that tells us about biological aging as a whole, but it is a complicated question that I don't really have a feel for at this point.
I mean, so first of all, I have to make a caveat here. I mean, so some of those questions, Peter, who is the originator of most of these ideas, right, would be able to probably answer more. Yes, Peter Fetcher would be able to answer more eloquently than me, and I have to be careful not to maybe misstate something. But so fundamentally, there is an interesting.
That's okay. The comment section will be sure
solve
to catch you out on that.
Absolutely, please correct everything, and I'm happy to learn a lot. But so, one of the things is there is a process called enslavement, which means that when you lose resilience in one dimension, because it now is a leading term, if you think about this in a physics context, if you make a like high-dimensional Taylor series, basically of all the processes, the thing that loses resilience is the thing that is always the largest term, right? Because it is not returning back to zero on average.
Okay, I see.
And so lots of things will get caught because they have some sort of nonlinear coupling. There's a combination, there's an effect of blood glucose on whatever, blood pressure, action potentials, like all sorts of things, even if it's higher order, like a nonlinear higher order connection. And if something loses resilience, then you will see this across systems, right? It will drag everything else with it, basically. Okay. And so that would mean that when you get to that point, you can probably see it in almost any parameter.
I see. Right? So let me see if I can restate this. So it's a human body, any animal is a system of systems. And if you lose resilience in one of those systems.
And it actually starts to fail. Losing resilience just increases the fluctuations.
Okay.
Right?
And it starts to go down the failure mode.
It will just drag everything with it.
Okay. So that's an early event, so to speak, that then
that's late.
Precedes the failure of the entire organism.
Yes.
And so we could think about this in terms of organs, like if your kidney starts to fail, eventually that's going to cause.
That's for sure true. But I think about it, maybe, for instance, use a society as an example, right? Like if you are in some sort of major crisis of governance, there will be lots and lots of, like, crime might go up, right? Like, and use of antidepressants might go up, truancy might go up, people might emigrate more. Any one of those parameters is essentially enslaved to the underlying failure of governance that you're having, right? And so you can tell something is wrong by looking at all sorts of metrics, right? Potentially even whatever, the kind of alcohol people are buying, or what TV shows they're watching, or what they're going on YouTube. So the idea is that once you actually get to a failure mode, you can actually tell that something is going on relatively easily by looking at different feature sets. And that's why, for instance, you might be able to see the same failure aging in an epigenetics data set and a clinical data set and a proteomics data set.
So what does it mean, though, that at least with the epigenetics, the current thinking is you can actually start to see this process very, very early, right?
Yeah.
How does that fit into this sort of a model?
I mean, there are two signals. One is the intrinsic stochastic process, right? So there is a signal. If you look at epigenetics, look at epigenetic clocks, where you do have just random sites relaxing, right? So they're hypo or hypermethylated, and as you get older, they become more alike.
Yeah.
Right? You think about, as an example, you take a long vector of zeros, and you occasionally randomly flip one 0 into a 1, then you do get a stochastic signal, and it's like coin flips. You will get an overall, the mean of one will go up, and between individuals, there will be an increase in the variance. Some have more and some have few flips by random chance.
Sure.
And that's Forsonian is the classic signature of just a random process.
I
see that as.
So you don't think it's anything more than just stochasticity?
No, I think there's more. I think that's a major part of the signal you see.
Okay.
And those are clocks. If you train just on that, in a stochastic clock, you're gonna get chronological age, right? Because you're basically saying, how much noise, especially in a okay. And then you have things where you get processes that actually start to fail. You have correlated change that has to do with some sort of process that is now no longer working the way it should, where you have correlated change, sets of things that are changing, right? And of course, they will signify whatever that process is signifying. So if that's related to blood pressure, for instance, because some methylation sites are related to something to do with blood pressure control, then you're going to see those, and you're essentially capturing a disease process, right? You're capturing an actual failure mode.
I see.
And those two things are overlaid. So that's why I always say with the current techniques, mathematical techniques, the current machine learning techniques that we mainly use, which is like regression, even PCA, we can't really distinguish those two things. We can't really, because we get an overlay, you get a mixture, right, of those two processes. And for instance, if you do a PCA, it will see correlated change in a whole lot of features, and that goes up with age, and it just drives variance or correlation in the data set. And you also see a random vector, which in the data set, you can easily learn and then say, okay, so this is a sampling vector, basically, that tells me how much stochastic change there were, right?
Yeah. Okay.
And so those two things are hard to distinguish or deconvolute with the current techniques.
Okay, so let me see if I get this. So with the epigenetic clocks, perhaps the reason why it appears that aging starts very early, in utero maybe even, is there's this underlying stochastic damage, we'll call it, that is being detected. And that could be purely random, right? Yes. And then as different systems start to go down this failure pathway, then you're going to see these correlated signals.
Yes.
But those are happening at the same time. Yes. And so the simplest way to model this is you've just got those two things and they're overlapping and you need some way to deconvolute it. But of course, and I'd be interested to hear your thoughts on this, the rate of stochastic damage can also change over time, right? And probably does.
Yes, it does, yes.
And so that's probably going to complicate things even more.
And it might respond to intervention, right?
Absolutely, Or an environment is an intervention. And
exactly.
And then genetic predisposition to damage could also influence that at the individual level.
And so fundamentally, that is this different in the damage accumulation rate or thermodynamic efficiency factor, right, between species, right? If you look at the rate with which this random events occur, they're different in different animals, and we know that the epigenetic clocks tell you different ages at different.
That's right.
For different animals.
That's right.
And so that's basically the idea, is that you can see those differences and they matter, right? But but they then lead to failure that leads to another type of correlated change that becomes eventually self-amplifying.
And so then, I think an interesting question is, do you think, and obviously it's speculative, do you think there's anything special about the epigenetic marks as a way to measure these biological aging processes? Or do you think you could accomplish the same thing using other types of proteomics, metabolomics, whatever? And I guess those aren't mutually exclusive. There could still be something special about epigenetics, and you could do this with lots of different types of data.
So personally, I mean, and this is a belief rather than a knowledge, right?
Sure.
I think you could do this intrinsically with any type of data, because the two things occur, right? Randomness is there. It might be easier to see. It's easier to see this in something almost digital like epigenetic marks than,
yes
for instance,
or no
blood
in terms of
pressure
methylation.
Or something. But even in the, if you look at the sort of clinical markers, you have red cell distribution width, which is essentially, tells you something about resilience, right? It's like it's basically trying to keep the distribution under all sorts of perturbation narrow, and it just widens, right? And you have HbA1c, which integrates over fluctuations, right? So those are very directly related to the sort of stochastic side to think, to the loss of resilience per se. And then you have SSBNP and things like this, which are organ dysfunction measures, which are basically telling you what is already failing, right? And of course, it's much lower resolution if you get 60 clinical markers than you do tens of thousands of epigenetic marks. But for me personally, I'm maybe most excited about proteomics in this regard, right? Because
why is that?
Well, because it's so interpretable, right? So if I can learn to see pathways and processes and readouts of things like resilience per se, I can possibly learn to deconvolute those two things, and I can make actionable predictions. I can say, well, here's your resilience factor, and here are the 5 systems that you're most likely to fail along. And so you can do very different things. You can, push back on the individual failure modes and say, this is the thing that will kill you. Let's have the screening test. And at the same time, you can say, well, which interventions might actually bolster resilience and keep you from, the stochastic, the entropic aging.
So let me do a follow-up on that, because I think if I understood you correctly, you're saying proteomics, you think, is going to be closer to the proximal cause, right? So if you can identify the proteins that are involved, that will be more likely to tell you something about the biology of the process, right? Did I understand that part correctly?
Well, possibly. Certainly the biology of the actual failure.
Right. Okay, sure, yeah.
The actual cause, right? So the interesting thing about the cause is that that's really really kind of a difficult problem, right? Like, because the thing is, why is the stochasticity there? Why is the entropy accumulating, or what controls this?
Yeah,
right?
right.
This might not be the thing that fails. In fact, it's almost certainly not the thing that fails, right? And I think, yes, to learn how to measure this is the first step to learn how to control it.
Okay.
But it might turn out to be something really surprising.
So I've got two questions about that. One is, why wouldn't the epigenetics also give you the same information? I mean, in theory, right, the epigenetic changes are leading to dysregulation in gene expression of factors that are involved.
And I have that slide, right? I start from the epigenetic clocks because they're the most well-known ones.
Right.
And I say, and this will lead to a change of transcription, and this will lead to the change of...
I guess what I'm wondering, though, is so far, people have sort of, shockingly failed to link the loci where the epigenetic changes are happening to anything that seems to be related to the biological aging process.
But I think, and I mean, this is really not my area, so I'm like, talking out of my ass here, but...
we do that all the time, don't worry about it.
But, I think it is non-trivial to assume that the epigenetic marks will directly relate to the genes that are proximal to them, even. Right?
Yeah, I guess that's true.
So, the genomics of it is a hairy problem.
Right.
And that even then tells you about transcriptional levels, possibly, but not really about actual circulating levels, right? And you do blood proteome, you know this protein is up, and you know what is the process that causes this, and it is caused by...
So it's going to be easier to deconvolute that connection if you're talking about the protein level versus the gene regulation level. That makes sense.
The proteomics panel, like we were working with a little bit now, has lots of cytokines, right? And you do all this that's inflammation. And you might even be able to say this is autoimmune and this is actual infection, right? And you could probably learn this from an epigenetic signature, but there's some more steps involved, I'd say. And so that's why I like proteomics.
Okay.
And also it's like, of course, it makes sense to explore something that isn't already having, very large efforts going on.
Yeah, of course.
Not trying to beat the people who invented it to their game.
Right. Okay, so the other thing I think I still am struggling with is, the biology of aging that we think we understand now, the hallmarks of aging, mTOR, insulin, IGF-1, all of that stuff. Where does that fit in? Is that affecting the stochastic damage accumulation?
So it will certainly do some of that, right? I mean, so I am sure that all the things that increase stress resistance and DNA damage repair and will have that effect. But whether interventions that extend lifespan affect the sort of amount of randomness, right, the stochasticity, or the intrinsic damage accumulation, or increased resilience in some way, I think we need to measure. So my point is, and I know Gero is working on that, to have different layers of experiments, right? Like if you do some things you might be able to in tissue culture, right? Like with single-cell RNA-seq, and some of that you need model organisms, and some of those things you might need clinical data, longitudinal clinical data. And once you validate that these parameters are meaningfully defined in those settings, you can then ask, how do I interfere with them? How do I control them? How do I make a drug for it? What lifestyle interventions affect it?
Yeah.
There's an interesting societal example of this. So Strehler-Mildewan relationship is this observation that if you take a country with a better healthcare system, more developed country, you have lower intrinsic mortality early, right? So lower childhood mortality, lower mortality at all stages of age.
Right.
But of course, the society hits the same maximum lifespan at 120. It's not actually affected.
Right.
If you take a country that has, maybe less well-developed healthcare systems, less sanitation, more mortality, this is done in the 60s, comparing different countries, you have a much higher initial mortality, but it also hits 1 at 120.
Yeah.
So if you look at aging rate, it's actually higher in the developed country, because you go from a lower intrinsic mortality to 1 in the same amount of time than in a country that has a higher mortality. Right? And so there's convergence, right? And you can do the same thing with wealth and education in like in NAINS and Haynes or Biobank, where you get that the initial mortality of rich, highly educated people is lower, but they hit 1 at 120.
Absolutely, yeah.
So all of these things would argue that if you want to model this in this paradigm, that wealth, education, sanitation, healthcare system, all of this lowers temperature. right? It lowers the amount of stochasticity you experience, and so while your resilience is there, at all ages, you have a better survival chance, a lower chance of getting sick. And this might even be like the exposure to inflammation, like infection, all of these things, better sleep. But you're hitting the same wall at 120 because you're not changing your intrinsic aging rate. Right.
So how do you think about that in the context of, some of these interventions that in laboratory animals that at least appear, given the conditions we do the experiments under, to increase both median and maximum lifespan of the population? So DAF2 in worms, sort of classic example, caloric restriction in mice. Is it because the conditions we're doing those experiments under are artificially depressing maximum lifespan, apparent maximum lifespan? Or is it that those interventions, at least in that context, are actually hitting both of these terms?
I mean, so there's an interesting point to start with, that the question is, are these animals actually ever stable, right? Like, so worms are a perfect example where, it looks like and the question the way to test this is to do perturbations and see how long do they persist, right? If you do a caloric restriction experiment in worms for a short while, or a heat shock experiment, and you get a lifelong benefit, that means there's memory, right? One event is memory. Absolutely. And this might not be true in people, right? And so in this paradigm,
which means sauna is not going to be a longevity intervention.
I like sauna, and it certainly probably reduces your now risk of certain things, but it might not make, it will not.
Probably isn't going to hit maximum lifespan.
You will not hit maximum lifespan, I'm pretty sure, and neither will cold plunges. But anyway, so then the problem is that now you're having a species that might be always unstable.
Okay.
Right, and then you get to
and what would be the experimental measurement to test that?
So an interesting example of a thing you can explain with that way of thinking is the DAF2 degrons that Colin Abel has done, right?
Yeah.
So yes, this really cool thing where you can wait until 75% of the cord is dead, and then you switch off DAF2.
Yeah.
And because unlike in the original Sintiakinian experiments where it was RNAi, which loses efficiency.
Or even the DAF2 mutant, where they go through development with DAF2.
Genau. Then now you switch it off late, you suddenly get the same benefit, right? Like they suddenly go onto the other trajectory.
The ones that are still alive.
The ones that are still alive.
Yeah.
And the way to explain this is that essentially you have the stochastic drift, right? So now there's no returning force. So in other words, the system just drifts. And some animals will just be lucky enough not to have drifted into failure mode, because they're still alive, right? Now, what the DAF2 degron does, is it increases the critical threshold. So if you think about the potential, it never looks like this. It always looks like this, right? But then the question is, where's the hole that they fall into? And if you look at this and you change this, then an animal that's still here has the same benefit whether it's been here for 20 days or for 1 day. Right? It takes the same additional time to go from here into the failure mode because you shifted something back here. Right? And so you can, without any need for rejuvenation, reversal of damage, a concept, very easily explain this data by saying, well, okay, so they're unstable always. But since there is no, there's just this drift, the few survivors essentially are indistinguishable, at least on that axis. They have other changes, right? Colin measured all sorts of stuff. They are indistinguishable from actually genuinely young animals, so they benefit the same way from this intervention that only kicks in once you start falling.
And that may be similar to what we see with things like rapamycin in mice, where you can start late in life.
And the discussion is, are mice, the problem with this, of course, it would suggest that worms and mice are not good animal models for aging.
At least that aspect.
At least for that aspect, yes.
Yeah. In which case, I mean, if that's all correct, which I hope it's not, that may suggest that it will be harder to find those same kinds of interventions that you could initiate late in life and have significant effects on at least mortality in humans. I think this may be a place where we need to decouple health span effects from mortality, because you could potentially get robust health span or functional benefits in certain ways without actually impacting mortality.
I mean, if you want to play within the model, then you would essentially hit temperature.
Yeah.
Right? You make a billionaire pill.
Right.
Yes. You're well until your late 80s. And then you very suddenly decline, right? That would be, this would suggest that it's actually possible to square the curve, right? Because by targeting temperature.
And I mean, I think if I understand sort of conceptually what Peter Fedichev has suggested, which is that many of the because of this sort of potential fundamental difference between worms and mice and short-lived models we use in the lab and humans and the way we age, that most of the interventions that we know about today might be more effective at sort of squaring that curve or improving Healthspan without having any real significant effect.
I mean, it might reduce frailty, is the argument, right? It will like have some benefits on the disease modes.
And potentially hit median lifespan, but it's just not going to hit maximum lifespan.
Exactly. And that, and it will be, because you're basically targeting specific failure modes. Every time you push one back, if overall resilience is low, you'll fall into another failure mode. And so it's this sort of whack-a-mole game, right? You're like developing one intervention after another, right? And that might be the problem.
Okay, cool. So I want to talk a minute about, go back to biological aging clocks, because I thought in your talk yesterday, you had sort of an interesting way of framing, what does a clock need to do in order to be useful? So I thought maybe we could walk through that. So,
I mean, there's a sort of proximal utility, which is just the predictive ability of the clock to tell you what's going to happen to you and what you can do about it, right? So, I mean, if you talk to people who want to use clocks in healthcare systems, in clinics, they basically want to know two things. What's going to happen to me? What can I do about it? Now, if you are a purist aging researcher, you want to, say, okay, can we distinguish that into disease prediction and detection and prevention and true aging differences? Right?
Sure.
Because of course, what we ultimately want, we want to modify fundamental aging rate. But in the first instance, I think what you need is you need to be able to do individual prediction. You need to say what will happen to you, and then you need to say why. And you need to say, what can I do about it? Because you're going to have that sequence of questions.
And I think also what may be wrong now, right? So detect existing disease.
Yes, detect existing disease, predict future disease, prognosticate. In other words, tell you what's going to happen to you under, in a certain situation, and then give you at least a target to hit.
Right, something actionable.
Something actionable, Right. Not necessarily that there has to be, a ready-made intervention for it, but, even just identifying a problem and saying if you could prevent this, you would live longer and healthier, would then open up, the chance to develop something for that.
And then I thought the other thing you said, which was interesting on top of that, is for these things really to achieve, maximum utility, there has to be, I don't remember exactly how you phrased it, but I'm going to paraphrase. I mean, there has to be sufficient evidence that that these things work, so that regulatory bodies are going to believe them, they can be used for intervention testing, for clinical trials. And so, how do we get to the point where we're able to gather that data set to actually be able to convince skeptics like me that these things are actually doing what they're supposed to?
I mean, accuracy and precision, right?
Sure,
So the point is like,
but accuracy is hard, because if we don't actually know what biological aging is, how do we measure it? But I think in this case, you're saying, well, maybe we don't worry about biological age or aging rate. We worry about the outcomes of disease, functional declines, and okay.
And if you have a problem with clocks, you can call them whatever predictors, right? Models, digital twins.
Right.
But the fundamental idea is that you will predict a measurable outcome, mortality, morbidity, functional decline, and you then expose yourself to a test. In other words, for instance, if you use mortality, you sort a list of patients in the order in which you expect them to die, and you compare them to the actual sequence to which they died. And that's an absolute metric, right? I can say I did a better job or a worse job at this. And in fact, there's an optimal function. You can say, well, how good could a perfect clock do this, right? Because I can run a simulation. I can say, here's the amount of randomness in aging. I know the mortality. If I assign these people, random biological ages, calculate the risk of dying, run the simulation 10,000 times, what is the best prediction performance I can ever hope to have? Because if I know your biological age exactly, whatever I say, you're like, 45, right? Then what do I say about your risk of dying might be very accurate, but then when you actually get the disease and die is highly stochastic still, right? I will never perform like a crystal ball.
Do you have a feel for what that is?
We actually have a little project trying to build that.
Interesting.
Right? Like a version of this. Because the question is, it's an interesting observation. We're playing around with these clinical clocks that predict mortality. And we've now made dozens of them, and we've also used the methylation clocks, and they're very similar in performance. The best ones are very similar. Some of them are not very good.
Performance assessed how?
In in predicting the order of death of people in the data sets that we're having, which we have 20-year follow-up, right? So we have a lot of mortality. And so basically, you basically say this will be the first person to die, and this will be, these will be the survivors, because eventually you censor them, right? And in this task, there are actually quite a few clocks that use different feature spaces, different mathematical approaches. We have done neural networks, we've done, and they differ, but eventually they're very similar in performance. And so one question we have is, how good could you actually get, right? Like, is this already, are we approaching asymptotically the best you can? Which I'm not claiming we are, but it's one of the questions that occurs to you is going like, are we actually hitting the upper limit of what predicting biological age can do? Because you haven't got a crystal ball.
And that's because of stochasticity in the system, just intrinsic stochasticity.
Because 4 people who are exactly 45 years old will not die on the same day, right? And so there's a maximum, and they experience different things. They're factors you don't know, right? They get depressed, they get divorced, whatever. Those things affect the trajectory, and you can't tell them from the cross-sectional data that you put in, right? And so that would be very interesting to say, okay, so what would the best possible clock do, right? I mean, that's the first thing. The other thing is, I think it's really important to make sure that eventually you get to the point where you can tell the benefit of a change in this number.
Yeah, I mean, I think that's one of the holy grails. There's probably multiple that we're after here, but yes, absolutely.
Tell the benefit and be so sure about that you can offset a risk. Right?
Yeah, go into that a little bit more. What do you mean by that?
Well, so for instance, I mean, today, if I say to somebody, go to the gym and lose some weight, I know that there are some risks to this, right? Like you could tear a tendon, there's a cost, you have to spend money on doing this, And I know that I can make that suggestion because I know the benefit of losing 20 pounds far outweighs these risks for most people, right? And we say, consult your physician and make sure that you But fundamentally, we know that the risk, the benefit outweighs the risk. But if I, for instance, say, okay, let's do this immunomodulatory cocktail, right? Like whatever, or like, SGLT2.
Or gene therapy.
Yes, untested gene therapy. Well, I mean, okay, you probably can, with relatively low effort, say that the benefit in this case. Anyway.
The risk outweighs the potential benefit, most likely.
Exactly. But so you need to have, it's a quantitative thing, right? You're going like, for 10,000 people that I give this prescription to, I can tell how many people will get a stomach bleed, right? Or how many people will get an adverse response.
But the clock isn't going to tell you.
No, but I know this because I know I know the intervention.
So you have to know something about the risk profile of the intervention.
Exactly. I mean, the perfect example is that mini aspirin. There's been an endless discussion about this, right? Is it lots of people get put on baby aspirin for cardiovascular protection.
Right.
But tests come out and like studies come out and say, yes, the bleeds are worse or better, or, it's worth it, it's not worth it. We change our mind about this all the time, right? And one of the problems is we're very slow with this because we have to wait for a 20-year observational study, right? And so in aging, that's not going to work. I'm not going to be putting 10,000 people on rapamycin and then figure out that actually the adverse events far outweigh the benefits. It would be great if I can put people for 1 year, measure a clock, and trust that number enough to say, okay, you're going to on average live 6 years longer, right? And that's the benefit. And now let's ask ourselves whether what we learned in those 2 years about adverse events justify, or allow this to be a justifiable choice. And I mean, nowhere near there, right? But eventually we'll need that. We'll need to make those decisions.
So you said we're nowhere near there. What makes you say that?
I mean, we haven't done a lot of prospective studies with these clocks under real-life conditions.
I see.
Right?
So it's not so much that the clocks today couldn't do that for sure. It's just we don't have the data sets yet to know whether they're able to do that.
I mean, stuff like what you showed where you do this.
Yeah, I mean, I think the direct-to-consumer stuff that's sort of a different beast because there's the incentives that go along with marketing to consumers that push companies not to do good quality control. But I think let's just say that this was these, epigenetic clocks. I want to talk about lineage and lineage 2 as well, but these other kinds of clocks that are being developed in the academic world, if those were, carried out under the best possible conditions, would the precision and accuracy be sufficient to achieve what you were just talking about? I mean, I don't know we don't know the answers.
Well, that's the point.
Maybe.
We don't know the answers. So I think we need large studies, not in a training data set, right?
Right.
Where you
Right.
have
In the
also
real world,
in the real world where
Yeah.
you measure people under different conditions. Maybe they
Yeah.
didn't fast even though you told them to.
Right.
There's
Right.
variability in the population that you're sampling. Maybe they're not all Americans born in sampled in 99, but
Right.
exposed to. So there's so many parameters we don't know, right? Whenever you take a model from one data set to another, performance can change, right? And you don't know why, right? And so this is even worse. There isn't another data set. I can't do some sort of batch correction when I apply it to new people, right? Because I only have one person when I sample the first person. How do I do batch correction for this, right? And so I think we need to, and we're doing this, right? We are starting this. We need to build cohorts. We need to follow them. We need to apply it. What if the people are sick, right? If you're hospital population rather than volunteers. And then basically say, what is the performance in real life situations in predicting those outcomes, right? And once we gain confidence that yes, when the clock says you're at high risk of these adverse outcomes, or the predicting algorithm, don't want to call it a clock, you are very likely to have experienced them. And if the clock says, you got much lower in your risk, then these things actually don't happen to you.
Yeah.
Right.
But still, aren't you going to run into or aren't we going to run into the challenge of how slowly humans age and how long it takes to do those sorts of, true follow-on assessments of outcomes? I mean, I guess you can, in a year, if you have a large enough population, get a pretty good feel for how accurate the clocks are a year out.
Yeah.
But that doesn't tell you how accurate they are.
That's true.
5 years out.
That's
or
true.
10 years
So
out.
one of the cool things, I'm really excited about is biobank samples.
Right.
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 So I think biobank samples are really cool because you can. It's almost like Indiana Jones archaeology, right? Like you finding this hidden truth from 20 or 30 years ago. And so, for instance, there's this really cool study called the Singapore Chinese Health Study, which they're well in excess of 10,000 individuals' frozen blood samples that are in a biobank. And if you find the money to do the omics, for instance, the proteomics, and these people are still being followed up, so we know exactly what happened to them.
I think that's the key part here, right? Is you're not relying on only biobank samples, but you can go back to the people who are still in the study today and look at their samples 10 years ago, 20 years ago.
And they're getting resampled, and there was a follow-up study where for over 1,000 of them, they did brain imaging and sleep studies, and so we know a lot about how their aging trajectory went. Right now, it's still a problem. We're doing something essentially cross-sectional. We have samples from 20 years ago, and we're predicting what happens to them in the future. We're better at continuous samples. We're going to have another set of samples now, but I think building those sort of data sets will allow us to fast track some of that.
Yeah. Okay, cool. So I want to finish up by talking about lineage, right? I know you've been doing quite a bit of work on this. So maybe you can take through, how does that clock work? How did you guys settle on the parameters that you settled on?
So we decided to go with a clinical clock for the exact reason we just
Maybe you can just define how is a clinical clock different from other clocks?
Okay. It doesn't require any complicated omics that is research grade, right? It uses standard parameters, questionnaires, medical exam, standard clinical chemistry. And the reason is that those things have been collected since the 80s. They are actually highly standardized. If you see how a hemoglobin test is validated, it's the high standards of reproducibility required to use them in a hospital. So they're very reliable data sets in this regard. And there's some very large data sets, UK Biobank and hence
because those tests have been used for decades. Those are the kinds of things we've got data on from the existing longitudinal studies.
So that was the first decision we made to go with that.
And I think the other thing that's useful, I personally find about those kinds of data as well, is because they've been studied for so long, we have some understanding of how they connect to disease processes.
Yeah, absolutely.
Right? And it's not like a methylation site where we have no idea why that methylation site is correlated with this outcome.
And we have drugs to impact many of them.
In many cases,
and we have idea of exactly like I say, pathology that might be driving this, right? So definitely that was one of the motivations. And it was a toy project. We didn't really have funding for it at the time. It was just Feng Shen, who's a brilliant geriatrician and longtime friend and student. On and off student of mine who keeps going off to medical school, come back. And he basically came back to the lab, and obviously he has deep intuition about these things too, right? Like if he looks at something, he goes like, oh, that obviously, is an active infection, right? This patient has an infection. I can't tell this, and from a proteomics data set, it takes a lot of annotation, but doctors are trained to read these things. So it made sense for us to do this. And then the other interesting thing is there are risk markers that exist on those. And so one of the questions was, can we do better than what, whatever the standard ASCVD score or, like this sort of, geriatric frailty score can do. And we thought it was, interesting to try, right? So that was the first thing, take this. And then out of the discussion we just had about failure modes, PCA is a natural way to approximate essentially some of those failure eigenvectors, right? So from a fundamental perspective, a linear dimensionality reduction by PCA, principal component analysis or singular value decomposition, is a natural choice to explore a data set, right? It might not be able to deconvolute the stochastic signal from the failure signal, but it will tell you the kind of correlated change that occurs in the data set. And you can approximate things under some conditions like, these failure modes, the eigenvectors, in which direction the failure occurs from them. And so the other thing, I was talking to Peter, and he said, oh, of course, his quote was, of course, the first principal component of any high-dimensional data set of an aging cohort of animals will always be aging. And I was like, there are many words in there, and I need to think about it, right? And so we basically started with a PCA as a dimensionality reduction. So we do a PCA, and we take, you have 60 parameters. You actually, initially, we had 160 parameters. There was DEXA scans and all sorts of stuff in the data set. And you get a PCA, and you essentially get different, correlated sets of features. We do a Z-score, so it's a correlation, not covariance. It's not driven by the magnitude of the parameter. And then we ask a Cox model, so Cox proportional hazard model, which is a simple linear risk model, which is commonly used in medicine. Therefore, it's easy to explain and to understand, to look at these PCs and determine how much risk they confer to the outcome, which is death. That's very simple. Now, PCA also...
And so this is all mortality at this point?
It's all mortality. All-cause mortality other than accident.
Okay.
And PCA also imposes orthogonality. It forces the system to be, the parameters, the dimensions to be independent, which is perfect for a Cox model because it makes the same assumption. So it is the simplest way you can do this other than just do a straight up, regression or Cox model on the raw parameters, which we also did, or doing. But it made sense from this perspective. And so the trick is that it was supposed to be a 2-week, let's try this out before we get some proteomics data kind of exercise, as often these things go. And it just worked so much better than we expected. And it was so much more interesting than we expected, right? You look at the PCs, and again, you have a medic sitting next to you, a consultant in geriatrics, and he looks at this and he goes like, oh yeah, I can tell what's wrong with this person. This is kidney failure, right? And I can tell, this is the prediabetes. And so you could look at the PCs and you're like, oh, so the PCs are actually capturing, as you would expect, but they're capturing common disease processes, right? It's like, there's not just one feature. It's like collectively they tell a story, right? So PC1 is always cardiometabolic inflammation. And there's a PC that's clearly driven by smoking, the kind of features that go up in heavy smokers caught by this PC, and it predicts COPD death, right? So you realize that this is a really neat way of dissecting the data set. And so we made this model and started benchmarking it, and it kept working better than really it had any right to do, right? Which is beating the standard risk scores, for instance. And we're like, well, why are people using this score and not a model like this if it takes us 2 weeks to make it, right? And of course, 2 weeks turned into 2 years now. We've done like many rounds of
annotation. You published a couple papers,
and you keep finding new ways of making it better, and new ways of exploring what it means, and it's become this journey, right?
And so are clinics now actually starting to use this algorithm?
Yeah. So we have the task to develop it for the medical trust that we're working with at NUH, at NUHS, and at NUS's hospital, or the hospital affiliated with NUS. And there we will apply it to medical data in the hospital, not to predict mortality, but probably predict things like readmissions or adverse events during surgical procedures. Because the idea is that if your resilience is low, you're going to have more, adverse events under challenge, or you're more likely to return back if you're released from hospital, if you're discharged. And so the idea is, can it be predictive in that setting? So we do that for sure. And then we have collaborators, Novi Health in Singapore, which is a very good clinic that specializes in things like, prediabetes, weight loss, metabolic disease, screening, and they have a longevity angle now. I mean, they're being pushed into it. They're more coming from the sort of classic health promotion side, and they're moving. and they want to apply it. And for instance, we will have a trial with them looking at whether their program, shifts.
That's what I was going to ask. Is it to the point yet where you're confident that it is predictive of intervention response at the individual level?
I'm pretty sure it will be. What I'm interested in, okay, so if you take the 5 top parameters in a person and you give them 5 drugs or 3 drugs for the 5 parameters, right?
Sure, it's going to move
it'll
in
move
that
those
direction.
parameters and it's going to get better. That's the question. What I'm interested in is whether we can do what we did in silico, where we do matching of patients, where you see benefits that go beyond the primary thing, right? Like, for instance, if you deal with high blood pressure causing kidney problems, do you then also see an improvement in metabolic function or in red cell distribution?
Right.
In other words, do you see PCs other than the one you push against respond?
And what are some of the key parameters that seem to be driving?
I mean, we're heavily loaded for clinical parameters, right?
Well, I know that, yeah.
So, like, things like,
But you said there were like 100 and some that you started
160,
with?
yeah. And we reduced it now to just under 60.
60. That drives the overall score or the...
Yeah.
Okay.
It's just the Lineage 2 is just using those.
Okay.
And there are, in fact, only 3 blood tubes. So 3 standard blood tubes. So for instance, we have the blood counts. So it's like, I forgot how many, Fengshan would know exactly, but like the different blood cell types, that itself makes something like 12 parameters.
Sure,
right?
Right, of course.
It's not 12.
Yeah, the different types of blood cells and their various amounts.
Exactly, and percentages.
Yep.
And those things are, they're not 60 tests, right? They're 60
absolutely.
parameters.
Yeah. So from a single blood draw, you can get
3 tubes, yes.
Okay,
yeah.
3 tubes, which isn't much.
Yes, yeah. And a urine tube and some questions.
And so there's a survey component as well. Okay.
And Fengshan has run his own trial, COG-H, on this with geriatric patients, and there we asked the question whether the clock is predictive of, adverse outcomes, like a transition from mild dementia to stuff like. It's still ongoing. We have too few outcomes to predict, but some of the observational things are quite interesting.
Yeah. And so a couple of interesting thoughts. One is like, I wonder how closely would the parameters that you settled on match up with some of the other clinical clocks that have been described. I'm sure they're going to be overlapping for sure.
I'm sure they will be, yeah.
And then are you able to predict, in addition to mortality, specific disease processes, or is it really focused on mortality?
We haven't done really disease processes per se because we don't have that much. Actually, we have sort of. Okay, so the logistic regressions against labels to do with disease work. So the individual PCs are predictive of patients already having a disease, right? Because we don't have forward-looking data, but we know that diabetics look diabetic.
Sure.
Right? And then the other thing we have is we have done the different individual causes of death, and the predictive ability is better for cardiovascular disease, but still works for cancer. So that we have done. And then we have done things like hand grip strength, gait speed, cognitive testing, independent activities of daily living, and it's predictive of that, of the current status. But of course, we haven't really done any long-term follow-up of patients that we measure.
Right. And in the process of going from 100 and some parameters to these 60, did you lose or leave out parameters because they weren't as predictive, or
both? I mean, so the stuff is correlated. PCs are good at picking up correlated sets of features, and so you realize
you don't need it all.
You don't need them all. And one process was to look at what's in different data sets because we wanted to do cross-validation, and so then we dropped things and we figured out the performance doesn't really get worse, but it's now we can test it in the other data set.
I guess part of the reason I'm asking is because going back to a concept that you talked about earlier, which is that you can probably get equally or roughly equally performing clocks, I'm just going to use that word, from a bunch of different data types, right? Could you, in theory, if you had high enough resolution, get a similar precision and accuracy for mortality from a whole body MRI, for example, as a type of data, right?
I'm pretty sure you could. I mean, I haven't tried it, and I wouldn't want to make algorithms for image analysis because it's a whole different kettle of fish. But for instance, on the other extreme, I know that Gero has a clock that's based on just fitness tracker data.
Okay.
Right.
Yeah.
Interesting. And again, it's dynamic aspect, right? If you think about it, if you get a cold, you're going to move less, right? But in your case, it's going to be 2 or 3 days, and you're going to be back. Right. That means you're high resilience, right? Because it takes you 2 years, 2 days to recover from a dip.
Right.
If you are older, or like after a gym, like the next day you're knackered, right? Whereas in an older individual, this will take longer, so there'll be a longer correlation.
Right.
And in a geriatric patient that's very low resilience, they may never fully recover, right? They drop and only do a partial recovery.
Yeah.
And those patterns directly can also give you a resilience measure. So I actually think you can, not to say they're all equivalent, right? They have advantages and disadvantages, but I actually think the feature space may be far less important than the algorithm.
So we're probably not, assuming all that's correct, we're probably not too far away from where you can wear one or a few continuous monitoring devices and have a real-time mortality predictor.
I absolutely think that that's true. I mean, so especially once the sort of non-invasive glucose metabolic measurements become available, like even ketone bodies.
Right.
And I think if you have accelerometer, oxygen, pulse, blood pressure, and a couple of blood chemicals, I think having it longitudinally at that resolution will far outweigh.
And you could get those measurements,
exactly.
really, really close together.
Will far outweigh the.
Cool. That's exciting.
Good.
Yeah.
All right.
Awesome. So, just to finish up, what are you excited to see happen in the next 5 years in the field? What do you see coming that's intriguing?
Well, I think one is having a sort of convergence of the clocks on something where you can measure, where you get the same answer from 3 different things and you can really trust it for intervention testing, right?
Yeah.
And in that context, then actual intervention testing with drugs, right? So I really want to see a human rapamycin trial with an outcome that is, we agree means something, right? SGLT2 inhibitor, Ozempic, so many things that people use already. Metformin, acarbose, ACE inhibitors. There's so much cool options which we think might work.
Right.
And if we can close the loop on those, I think we can make a real difference.
Yeah. And I think especially at the individual level, right? Because I think probably none of these things, assuming that they do modulate the biology of aging in a positive way in humans, probably none of them are going to work the same way in everybody. And certainly there are going to be different individual dose responses. And so the only way you can really get to that level of precision is if you have a way to monitor outcomes, efficacy, likelihood.
Exactly. And I know this is much fluffier, but a lot of people do a lot of exercise, probably do too much exercise. And they could make
the wrong kind of exercise.
And they could make a much bigger difference to their health if they actually slept more. Right. And so I think those sort of things, once you close the loop on this and you can basically say, no, for you, going to the gym a 5th time a week is not actually helping, would be super exciting for me as well.
Yeah, cool. Awesome. Well, thank you so much. This has been a lot of fun, and I'm sure we have given the viewers a lot to think about. I know you've given me a lot to think about, so really appreciate it.
All right.
And thank you for watching the Optispan podcast. As always, leave your questions or comments below. You can correct Jan on whatever he said wrong. And we hope to see you next time on the podcast.